Hello, welcome to another video on algebraic topology. In this video, we shall discuss the concept of a retract and the retraction, which is defined on a space. The definition is a space a subspace. See, A is a subspace. We take a subspace A. A subspace A of a topological space X is called a retract of X. A subspace A of a topological space X, so topological space X is a retract of X, provided that there is a continuous function which is defined, continuous function f defined from X to A, for which fa equal to f of A equal to A for each point A in A. For each arbitral taken point A in A, f of A equal to A. The retract on the function f is called, the function defined on X which possesses this property is called a retraction of X onto A. So that function is called a retraction of X onto A. See some examples. In an annulus, we consider an annulus, both the inner and outer circles are retracts. In the case of an annulus, see, the inner and outer circle both are retracts. We can take A as A equal to the collection of points x1, x2 in R2, such that A square is less than or equal to x1 square plus x2 square is less than or equal to B square. And then we have the inner circle. See, the inner circle, A is the space, original space, or the given space, and we take the inner circle. We can define the inner circle D equal to set x y in R2 such that x square plus y square equal to A square. It's a deformation retract of A. Then we can show that it's a deformation retract of A. So previously, in a previous video, we have seen that it's a deformation. Actually, it is a deformation retract. We can show that we have proved that in a previous video. But here the retract also works in a similar way. So since it's a deformation retract, there we have selected a function. We have proved that there exists a function. We have shown that a function there exists, or a homotopy there exists, which maps the entire space, the space A to the inner circle D. Okay, and that can be that homotopy can give us the required function as mentioned in the definition. Okay, so there exists a deformation retraction. So what is the deformation retraction? How can we give that deformation retraction? So yeah, there exists a deformation retraction. We use the help of we seek the help of that deformation retraction to prove that, or to establish that there exists a function, and there exists a function which is a retraction. So there exists h from A cross I to A with hx0 equal to x and hx1 equal to d, where x an element of A, and hxyt and hyt equal to y for all y belonging to D and t belongs to I. Now we define h from, based on this based on the existence of this this deformation retraction. We define h from the function h from A to D by hx is equal to, see, hx1. Hx is equal to h of x is equal to hx1, where hx1 is the one level, first the level 1 of the homotopy. So therefore h is continuous. Since h is continuous, since h is continuous, and then small h is also continuous. Okay. Also for A belonging to D, for A in D, hi equal to ha1 equal to A, and therefore h is the required retraction. Similarly, the outer circle we can define. In the case of outer circle, x square plus y x1 square plus x2 square equal to b square is also a deformation retract of A. In a similar way, we can prove that. Therefore, the one level of the deformation, retraction form a retraction. Okay. Next example, a closed subinterval. See, consider we consider the closed subinterval AB of the given interval. A closed subinterval AB of a given interval AB is a retract of AB. A closed subinterval, any closed subinterval, yeah, here it is a CD actually. The closed subinterval CD, we take it as CD of a given interval AB. It becomes a retract of AB. Third example, the set of endpoints. The set of endpoints, that's A equal to the set AB, is not a retract. So this is a non-example. It is not a retract of the closed interval AB. See, when we consider the endpoints, the endpoints A is equal to A comma B, the set A comma B, and we can see that it is not a retract of the closed interval AB where A less than B, because the closed interval AB is connected and A is not a connected set. But see, the closed interval AB is connected, but A is not a connected set, and then there cannot be a continuous function. So it is impossible to exist a continuous function from the closed interval AB to A, because A is disconnected. If there exists a continuous function from the connected set AB to the disconnected set A, then we get a contradiction. Okay. Every deformation retract is, see, every deformation retract is a retract. So there is a relation, it's a connection between deformation retraction and retract. Every deformation retract is a retract is a retract. So retraction is a, see, the retraction is the one level of the deformation retractions, because that retraction is the one level of the deformation retraction. But the converse is not true. Why? For example, a single point, see, a single point in S1 is a retract. A single point in S1 is a retract, but a deformation retract, but it is not a deformation retract of S1. See, it's a the single point in S1. If you take a single point in S1, then it is a retract. You can we can show that it's a retract, but it is not a deformation retract of S1. Okay, and it's illustrated. The reason is provided using that fundamental group. There is no direct way of see. It is not given. The direct way of proving this is not given here. See, but we use, instead of that, we use the method of ease. We use the help of the fundamental group of the two spaces here to show that. This is not it's a retraction. See, the single point is not a retract. It is not a deformation retract of S1. See, so for that, here we take the subspace D equal to x naught. Let's take D equal to x naught, and also x naught is an element of S1, and we can take capital A equal to S1. And we define a function f from, suppose that there exists a retract. Suppose there exists a retract f from S1 to x naught. Yeah, it's a retraction from S1 to, suppose f is a retraction from S1 to x naught. Then but we have we also know that pi 1 of x naught, it's a trivial group. Pi 1 of x naught, since x naught is a single point, so it is a trivial group which contains only the identity element. But pi 1 S1 is equal to Z, and that's also already proved. It's an established fact. This is it is not isomorphic, but naturally, if they are, if it's a retraction, if it's a retraction, if f from S1 to S1, S1 to x naught, suppose it is a retraction, then we must get the relation pi 1 of x naught is isomorphic to it. We must get pi 1 x naught is isomorphic to pi 1 s1, but it is not the case. Really, it is the nulls. It's the empty. It is the single element group. It's the trivial group. The first group is the trivial group, but it's not the trivial group. It is it's an infinite group which contains all the additive group of integers, and therefore actually we have the relation, a non-isomorphic relation between these. So due to this contradiction, one way we get the equivalent, the isomorphism of between these two groups, but the other way we get they are not isomorphic. Actually the groups are not isomorphic. We get the contradiction. Therefore we can correct the our loosely chosen assumption that there exists the point, single point is a deformation retract of the assumption that we have assumed. The single point is a deformation retract of S1 that was assumed. That is not correct. So okay, okay, thank you.